right, good morning. My name is Eaglin. My SMT is going to be over refrigeration systems with a little concentration on evaporative cooling. So I'd like to talk about the types of refrigeration systems, go into a little bit of the history of evaporative cooling, its theory, the refrigeration cycle associated with it, and any important formulas that associate with evaporative cooling. So there are four types that are found of refrigeration systems. There's evaporative cooling, there's mechanical compression, there's absorption, and there's thermoelectric. So mechanical compression refrigeration is typically what we've been going over in these labs and doing research on. It's typically found in refrigerators, freezers, or HVAC systems. Where we'll have a compressor which will compress your gas and excite the molecules and passes it along as a high pressure, high temperature vapor to a condenser, where the condenser releases heat to its surroundings, in turn turning that high pressure vapor into a high pressure liquid, which then goes to an expansion valve that ends up taking that high pressure liquid and converting it to a low pressure, low temperature liquid, which then goes to your evaporator, where your high pressure liquid cools rapidly and evaporates and turns into a low pressure gas, then repeats the cycle again. Also too, typically these heat sources in these systems are electric. So moving on to the absorption, this is pretty much similar to the same thing as the mechanical compression, except it uses a burner for its heat source here. So you'll see these typically in campers, RV setups, etc., where we have a generator that's typically a mixture of a refrigerant and a water, where the burner heats it up and it separates. The refrigerant gas separates from the water, turns into a high pressure vapor, and goes the same thing as your mechanical compression into a condenser, where it releases heat to the surroundings again, and follows the same process of an expansion valve and into an evaporator. However, in this process, there's an absorber in here that's typically filled with an ammonia fluid that ends up mixing, that goes back into your burner. All right, the third one that I found is the thermoelectric system. This takes two conductive plates and it creates a temperature difference whenever a battery source of power is attached to it. What it does is that temperature difference creates a hot side and a cool side. What you can do with this is, if you want to cool a room or a certain area, you place the cool side next to that area, and the heat draws through it, pulls it out, ends up leaving your leftover space or your medium cool. This is all based off of what's called the Peltier effect. I hope I said that right. And these typical applications you'll find in like lab experiments. With lab equipment, wine refineries, medical devices and coolers, and also in the aerospace industry. All right, so on to evaporative cooling. So a little history on it. It was originally, principles were in the 2nd century AD in Asia, where you have guys who would take a pot of water and that water evaporate, leaving cool air. They would fan that air over each other. It was the first concept of it. And then in the early 1900s, we had the electric fans that were introduced, where they would take a wet sheet and hung that in front of fans, where they would do the same thing. It would evaporate and you would blow that air as a cooling process. So real quick before I get into that, I started thinking about it. If you ever take a wet towel, set it onto it and it's hot, set it onto a counter, you come back, it's cold. It's evaporated to the air and left that towel cold. So it's pretty much the same process, something similar to that. So in 1936, whenever in the 1900s, when the electric fan was produced, we had Oscar Palmer was the one who created the what's called the swamp cooler now process. And in 1936 is where it started mass producing this product in Arizona, Phoenix, Arizona, where it came into production. So a quick question of why they're sometimes called swamp coolers. It's not stated who actually came up with it, but it was said that if you don't clean out that bucket of water, it ends up getting bacteria in there and ends up smelling like a swamp. So that's where it became known as a swamp cooler. All right, so evaporative cooling, there's no refrigerant required, no burner required either. So you have an evaporation process. So you have water placed over a medium or surface, and where that air passes over it, and through or over it, the air passes and the water evaporates into the air. This absorption is the next phase of it. The next phase is where water absorbs from the heat in the air, and it changes from a liquid to a vapor. This heat is absorbed, which reduces the temperature into the air, and it causes a phase change in the energy. And then, so that leaves the cool air, where a fan blows that cool air through a space through forced convection. Real quick, I tried to find, the refrigeration cycles for evaporative cooling process. This is typically more of your refrigeration cycle, where there's a complete cycle for the mechanical compression. On the left is a pH diagram for the evaporative cycle. The reason why I believe I couldn't find something similar to this for the evaporative cooling process is because it's not a complete cycle. The only way that cycle starts off, because in an evaporative, it goes into the atmosphere around. So the only way it starts back over is through your water process at the beginning. Here's some quick equations, formulas for evaporative cooling. You have your evaporative cooling capacity, which takes your mass flow rate and your latent heat vaporization into account. You have the work of a compressor, where you have your mass flow rate, your enthalpy of an inlet refrigerant. That actually probably should be in there, sorry. You have your evaporative cooling effect, which is the dry bulb temperature of air, your equilibrium temperature of the wetted surface, and then your wet bulb temperature. And then one more is your fan consumption. Obviously, you won't like to know what your power is from your fan due to your mass flow rate of air, your change in enthalpy, and your inverse of your efficiency of your fan. Here's my references.